Okay, so this is week number 6. We will cover Perceptron. This is a continuation from the previous session in which we study neural network. That is a basic foundation of deep learning. For this week, we will look into Perceptron. So Perceptron is a single neuron that is used for classification, binary classification, which means two classes classification. Okay. Remember when we performed the prediction last time, we are looking at a linear model in which we can draw a line that will separate the two classes. So when we talk about linear function, we will look into the general form with k variable. So k variables referring to the k number of attribute that you will be using in your data analysis. Okay, so k here refer to number of attribute. Okay, so if we have this one, so x1 up to xk, so we are referring to k number of attribute. So this is your attribute or your field. Okay. So for the linear function, we should have a formula in which we have all the variable here, and this is the summation of all the product of the value of the attribute to some kind of coefficient, okay, and plus the bias. Okay, so if we simplify this formula, we will have something like this, in which the m here referring to the coefficient, but in Perceptron, the m here refer to the weights that we want to estimate for each of the variable or attribute that we have. So this is the bias that we use to adjust the error. Okay. So in regression analysis, we are looking at drawing a line that will reduce the error between the actual and also the predicted value. So we want to draw the baseline that will reduce the residual. So kita punya formula is y a. Let me erase that one. A x plus b. So this is the slope kan, and this is the interception when x is 0. So this is the coefficient that we want to estimate. So this is in linear regression. But in classification, we want to draw a line or a plane or hyperplane that will separate these two classes. Okay, so we need to learn a linear function that will separate instances of different classes. Okay, so this is -1, this is +1, meaning that this is positive case sample, this is negative sample. Okay, so a linear function divides the coordinate space into two parts. So every point is either on one side of the line or plane or hyperplane or the other. So which means that you only can perform this for two classes, binary classification. So we call them the positive class and also the negative class. Okay, so when we look at the linear classifier, the output could be belong to -1 or +1, meaning negative sample and positive sample. So this is positive and this is negative sample. Okay. So for linear threshold units, they classify a sample X using the following classification, in which they are looking at the weightage and also the input, and this is the bias lah. So the output that we get here will depends on the value that we have here. If the value are greater or equal to 0, then y will be 1, positive sample. If the value for this expression is negative, so we will predict y as negative. Okay. So this is for the perceptron. Since we only have one neuron, so they will have a few input here, and then the neuron will process and it will give a sign here. So if -1, they belong to negative sample, 1 will refer to positive sample. Okay. So the geometry of linear classifier can be illustrated as follow. We are looking at the positive sample here and also the negative sample here. So this line, because we have two variables here, x1 and x2, because this is in 2D, two-dimensional. So the weight here is obtained from here. How much you want to move the x and y. Okay, so we only care about the sign. Everything on this line and above will be positive. Everything under this line will be negative. So this is only in 2D, okay, because we have two variables here. Okay, so in n dimension meaning we have n variable. Okay, a linear classifier represent a hyperplane that separate the space into two half space. So we are dividing the space into two parts. 3D, we can imagine three variable, but four variable and above, we cannot visualize. It's beyond our imagination. Okay, so for this example that they show on the slide, this is for the 2D. Okay, so when was perceptron first researched? Okay, they were established in 1958. Long time ago, people already thought about this. Okay, the perceptron, a probabilistic model for information storage and organization in the brain. They want to imitate on how human being functioning. And the first machine of perceptron was built in 1958 called IBM 704. Okay, that can play chess lah. That can be trained to play chess. Okay, so imagine in 1958, people already discussing about this, doing research about this, and that is the beginning of perceptron. Okay, so they are introduced by Rosenblatt in 1958. So the goal is to find a separating hyperplane that will divide the two classes, and this is an online algorithm in which they are taking the sample batch by batch. Okay, one sample at one time. Okay. Okay, perceptron is an algorithm for binary classification. So for two classes only. So we say that If the output is 1, so that means this is true. But if the output is -1, that means this is true and this is false. Okay. And a perceptron is defined as basic building block of neural network. This is the basic building block because we only have a single neuron. Okay, so we have all the input here, and also we have all the weightage here. So the output y will be positive if the value of this expression is greater than or equal to 0. Okay, and it will be -1 if this expression is less than 0. Okay, and we look at this w here. For linear regression, this is coefficient, but for the perceptron, this is the weightage. Okay, so this is what we call the weights of each of the attribute that we have in our model, in our data. Okay, so if this is exactly 0, the output will be positive. So this is the default. Okay, so instead, the value will be -1. In the same way that linear regression learn the slope parameter to best fit the data point, Perceptron learn the parameter to best separate the instant. So they will adjust the weight here in order to be able to separate between the positive and also the negative. So what happened is, um, let's suppose we have this example. We have four input here. So the first one is recently searched refrigerator. Second one is recently searched refrigerator review. And the third one is recently bought a refrigerator. And fourth one is has clicked on any ad in the recent past. So suppose we want to predict whether a web user will click on an ad for refrigerator. So which is this one, based on this feature. Okay, and the value of each one of these is 1 or 0. Okay, so let's suppose we have the weightage for each of the input that we have. Okay, and the prediction is positive if is 1 if the value is greater or equal to 0, otherwise -1. Okay, let's suppose we have this one on. Okay, so that means the rest is 0 lah. So this is 0 1 0 0. Okay, so we only have this one as 1 and -9, so this is the bias. Okay, so we will get -1, so our prediction will be no. Okay, next example, if we have two of these, so the value will be 1. So your prediction will be 1 because this is greater than or equal to 0. Next example is, what if we have these 2? So the value will be 4 here. So how do we get 4? We get 1 and 1 here times, okay, and add, we get 13 minus the bias here, 9. So we get 4. So this is greater or equal to 0. Okay. So our prediction is yes lah, positive. Okay. Let's suppose none of them is, okay, let's suppose we have 3 of them. So we will have -11 here. Prediction is no. Okay. If none of them is 1, so by right we only have minus 9. Okay, so the default prediction is that they will not click. Okay, so this is no. Okay. So this is a simple illustration on how they decide or make prediction based on the given weightage here. So this is the weightage that will be estimated throughout the learning process when they perform the um, training, um, trying to adjust the weight of each of the input that we have. Okay, so how did they process this value? How they get the optimized weightage for each of the input that they have for the perceptron? Okay, so I started with this. Initially, all weights will be initialized to be 0. Okay, so they will iterate through the training data. For each training instant, they classify the instant. Okay, if the prediction was correct, they will not do anything. If the prediction is wrong, then they will have to modify the weight by using the update rule. Okay, so if the actual and the predicted class are the same, so you don't do anything. But if they are not the same, that means you have to adjust the weight. Okay, and this one will be repeated for some number of times. Okay, so how that they update the rule? Okay, so for example, if the classifier predicted as instant was negative, but it should have been positive, so the current is this is negative, but you want them to be positive. Okay, so what you need to do is you want to adjust the weight so that this function value move towards positive. So for you to move from negative to positive, that means you need to add 2. Okay, so on the other way around, if current your current class is um, positive, that is positive, but your actual class is negative. So you want to reduce this one so that it will become negative. So this is minus 2. Okay, so you want to move the weightage so that it will go to the other class. Okay, so for example, this is the weightage that we want to update. This is your true label. Okay, so this is your true label. So this is your predicted label. Okay, and this is the value of feature j. So this is in our previous example, it could be 1 or 0. Okay, let's assume that this is 1. So it all depends on this one. Okay, the term is 0 if the prediction was correct. That means they are the same. So if these two are the same, so this minus this, you will get 0. Okay, so that means 0 times 1, you get 0. So you will not update your weightage here. Okay, so the formula here is Wj equal to Wj plus yi minus fxi times xij. Okay, Okay, but if the prediction is wrong, so um, this term is +2 if your true label is +1 and this is -1. Okay, so since you want to go from here to here, you need to add 2. But if you look at the formula here, +1 minus -1, you get +2. So this one automatically will add up to the weightage here, um, and it will update by 2 +2. But if the other way around, if your true label is -1 and your predicted label is +1, okay, so you want to move to this direction. So what you need to do is you need to add up this one by -2, then you get -1. But the whole expression is -2 already. So which means you will update the weightage to have -2 here. So that's how they make the the updating of the weightage. So depending on what you have for your prediction, and you compare with the true label of your instance. Okay. Okay. This one is the explanation. Okay. If the prediction is wrong, so that means um, your true label is +1, your predicted value is -1. So what you need to do is you need to +2 here. So you will increase the weightage. But if your true value is -1, your predicted value is +1, so you need to -2. So you need to decrease the weightage. Okay, and if they are two the same level of class, so meaning that they're 0, so you will not update the weightage here. Okay, but if this is negative -1, uh, the sign of the update flip means the other way around. Okay, so if we translate them into coding, pseudocode, so what happens is that we will have adjustment here. So if the y is +1 and the predicted value is -1, so you need to make them small. So this one is small, so you need to make it bigger. So you need to make it +1. But if your true label is -1 and your predicted one is +1, you want to make it small. Okay, so this is how you make them small, and this is the formula. And if there are no, if the y and also the true if the true label and the predicted label are the same, so that means no changes. Okay, so you will repeat this process. Okay, so that's how they update that one. So what about the b? So this is the intercept of the linear function, and this is what we call the bias. So the common implementation will be like this, in which we will have a constant that will be multiplier here. So if you add an extra feature to every instant whose value is always 1, then we can simply write this as this one. So which means this is considered as constant. Okay. Then we can update this parameter the same way as the other weight. So another thing that we also have to look at is the learning rate. But before that, let's take a look at this one. So this one is linearly separable. This one not linearly separable, the same as this one. We cannot do this. Okay. So if the training instant are linearly separable, eventually the perceptron algorithm will find the optimized weight W such that the classifier gets everything correct. Otherwise, it will have some prediction wrong. For example, like this one will be wrong, and this one will be wrong. Same thing like this. It depends on which side is positive and negative. So you have many wrong prediction that you will be made. Okay. Let's take a look at this one. If we look at the AND gate and also the OR gate, based on the value that we have here, because this is your input. Okay, this is your output. Okay, this is your output. This is your input. So if we try to make or draw a line that will separate them, this is the line that we can get. Okay. If we try to illustrate the OR function, so the OR function, the y will be 1 if one or both of them is 1. So we can also draw a line here. But for the XOR function, this is a situation in which we cannot find linear separation. Okay, so for n and all function, we could find a line that will separate them into two classes, but the XOR function, it is impossible to get the linear separation. So for this one, perceptron cannot be used to make prediction. Okay, so like I mentioned just now, those training instances that are not linearly separable, the classifier will always get some prediction wrong. So somehow you need to have a stopping criteria, and they are sometimes called maximum number of iteration or epoch. Okay, so you must be able to specify how many number of iteration that you want to perform the updating of the weightage or epochs, number of epochs. Okay. Okay. Another thing that we have to look into is the learning rate. This is your function just now, and we have add this symbol. So this symbol is a learning rate. This is just or step size. They consider this one as a step size in which it will tell you how large you want them to add the weightage. Okay, so in most cases they are 1, but sometimes you may want to speed up the process of learning. Okay, but to choose the step size, if the learning rate is too small, the algorithm will be slow because the updates won't make much progress. Okay, but if the learning rate is too large, the algorithm will be slow because the updates will overshoot and may cause previously correctly classification to become incorrect. Means they will not find the best one. remember that when we have the gradient descent, so if you want to adjust the weightage too fast, you will get you will not get at the lower um, cost function, because we want to minimize the cost function kan. So when we want to update the weightage of each of the attribute, you want to make it small or big. Okay? And this illustrates how perceptron work. So they will try for each sample, they will adjust the line. You want to see again? Okay, so it will slowly move the line that will separate uh, the two classes. So this is during the training, and this is during the testing. Okay, so finally they get a line that separate those two classes. Okay, in summary, we learned the prediction function for the perceptron, in which they consist of +1 and -1. During the learning process, they initialize the value to be 0. So it will use the update rule in order to update the weightage depending on whether the prediction is correct or wrong. Okay, so we will repeat this stage 2 until the perceptron correctly classify every instant or the maximum number of iteration has been reached. Okay, so that is the knowledge of perceptron that we get so far. Okay, but when we talk about multi-class perceptron, okay, just now we talk about a simple one, a simple perceptron that will do prediction for two classes. But for multi-class perceptrons, basically we are combining a few simple perceptron here. So in this case, we have 5 classes lah. Okay. So let's take a look at a simple example that we can apply the multi-layer perceptron. So in this example, we'll be using the R software. So and we have 3 classes here. Okay, 3 classes, and then we have 4 attributes. Okay, so they are all in numerical value. Okay, so we load the data, and then this one will show you the first 20 row of data. Okay, and for this one, we only take the sepal and petal. So sepal and petal length only. So we take this one, this is 1, and the petal length, and this is 2. Basically, column number 3, and then 5, column number 5. Okay, and then we will be able to show. Okay, so this library is used to plot the variable petal length and sepal length depending on the species that we have. So this is the command that we have. So we are plotting the Irish subset. So we use X as the sepal and the Y as the petal, and this is the color that we have, and also the shape. Okay, the size is 3, and this is the title. This is the X-axis, Y-axis. Okay, so as always remember that when we want to perform the classification, we have to be we have to somehow um, be able to normalize the value um, before we split them into training and testing data. So over here we define the Euclidean function. So this is used to measure the distance. And then this one is used to find the distance from the plane. Okay, so um, this is the bias that we have. So this is the summation. Okay, so what happened here is that when we want to perform the uh, linear classification, so we will find the distance between the each of the instant that we have to the plane that we have. Okay, so so over here, if the distance is less than 0, so less than 0 meaning that they are minus. If they are equal to 0 or greater, they are positive. Okay, so for example, if you want to find the distance from this point to this plane, okay, so basically we just plug in the value, okay, and this is the distance. So in this case, positive, since the distance is positive, so you will pass the positive here. Okay. So the function that we have here, the classifier linear, is used in here. So this is the perceptron program. Okay, so what happened is you pass in the, let me erase this. Okay, you pass in all the input that you have. So this is all the input you have. This is your uh, output, and this is the learning rate. So the default is 1. So you initialize the bias. You this is the number of times you update the weightage. You initialize the weightage to be 0, and then what happens is that you go inside here as long as um, you will be repeating this one as long as you have the predicted value is the same as the actual value. But if they are not the same, so that means you will continue, okay, because this one will make it true. Okay, first you put this one true, meaning that, okay, I will do this whole thing, the whole thing. I set this one false. So in case I found that some of the actual and also predicted label are not the same, I will have to do the adjustment of the weightage here. Okay, and this one will return you a list of the weightage and the bias, and also how many times you update the weightage. Okay, so if we look at the the value for x and y, so we will extract the value for the x, which will be the sepal and also the petal. Okay, two values into your x, and your y will be the species. Okay, since we are doing the um, binary, so we are looking at this only. If they are the same, we will call as positive. If not, negative lah. Okay, so when we plot when we call the function perceptron here, So basically we are sending the X here and also the Y, and we get here. This is the another. Okay. So when we draw a line here, based on the P that we have generated here, okay. So basically we are able to draw the line based on the value of the intercept and also the slope. So the value of the intercept is based on the weightage and also the bias. The slope will depends on the first weight of your variable x1 and the second variable of the x2. Okay, so this is how you perform the perceptron classification. You'll be able to plot and draw the line, the optimized line. Okay, so the term MLP does not refer to a single perceptron. Rather, they are containing many perceptrons that are organized into layers. So if you can see that you have the few input here, and then if you have multi-layer, meaning that we have the first one is this one, and then the second one is this. So basically they are divided into layer of perceptron. So MLP are extremely useful for complex problem. They make good classifier. They can be used for speech recognition, image recognition, language translation. They can also be used for creating mathematical models by regression analysis. So you can also use this one. So in R, we use this MLP function to create an MLP. So we have the X, which is the input, Y, which is the target value or the output. This is the size of the hidden layer, maximum iteration. This is the activation function for all hidden unit. This is for the output unit. This is a matrix with input to test the network, and so on. So these are the um, documentation for the MLP. Okay. So we will repeat the same thing again. In the previous example, we only use a simple perceptron, but this is how we perform the multi-layer perceptron. So the iris for the iris dataset, we will use we take a sample, okay, and we separate the input and the label. This is column number 5. This is column 1 to 4. So all the input will be in the iris values, column number 1 until 4, and then all the target will be stored in the iris target. Okay, so now we have X and Y. Okay, now we want to split them into training and also tests. So we will have 85% for the training and 15% for the practice. Okay, so whatever data you have here will be carried here. So meaning that we will normalize the value. So remember that we have to normalize. It could be using the scale or the min max method. Okay. So the MLP function can be called with the training dataset to build the model. So we use this term MLP, and we have the input training here, and also we have the target training here, and the size of your hidden layer will be 5. Your learn function parameter 0.1. I think this is the learning rate. This is the maximum number of iteration. this is your input test, and then this is your target test. So basically we have the train and also the test. Okay. So when we summarize the model and also we look at the weightage matrix, we have uh, this graph. So this graphs are saying that the more iteration you have, the sum square error will be reduced. Okay. And also when you perform the prediction, you will have the, okay, this one will plot the regression error. So the black one is the during the training. So this is the error one, the red one. So you can estimate the error that we have, how far they are not in correlation with each other. Okay. So we can also construct the confusion metric by taking into consideration the target training and also the values of the actual model. So basically we have all of these are true. Prediction, the error that we have is only this and this. So 5 lah. And for this one, this is during the training and this is during the test. This is during the training. Okay, so during the test, we only have 2. So 2 out of 23. This is the error. And for this one, this is 5 out of, have to add up all this lah. Become 45, and then 43, 39. So we have around 7, 1 to 7. Okay, 5 over 1 to 7. So this is the error. So this is the error during the training. This is the error during the testing. So you can perform a simple perceptron prediction, or you can perform a multi-layer perceptron in R. And this is the ROI, receiver operating characteristic. I believe you have studied this one in data mining. So this one tell you how good is the model. So what we wanted to do is we want to maximize the area under the curve here. So if you notice that this one is um, the ROC for the training. So this is the ROC for the test. Okay. So for the training, your model is good, but for your testing, because we have reduction here compared to here, this one cover more area here. So what the more area you cover under this graph, the better is your model. Okay, so that's how you compare these two, the performance during the training and testing using ROC. Okay, so this one is we are trying to use different method. Okay, and we have different parameter here, and as you can see that we will have different error here. So the problem with the neural network is that they have so many parameters that we have to try to optimize the value of the prediction. So the range of value are many. It depends on the parameter. So I advise those who are doing prediction using neural network or perceptron, you list out all the parameter and you list all the range of value that you want to test, and you perform a combination of those parameters. So it will take longer time, lah. But that's will worth one FYP for your final year project, lah. Okay. So in the next session, we will try to go over this practical. Okay. So in summary, we have learned the concept of perceptron, which are the basic building block of neural network. So we could have a simple one, or we have a multi-layer perceptron. We discover the linear separable classifier and the function this concept applies to. So what function we have? We have y equal to the transpose of the weight times the x vector, which is the input plus the bias. And also we have the learning rate here. We also learn a simple perceptron implementation function in R environment, and then we learn how to train and model them, model MLP as well. Okay. Okay.